Hello everyone, my name is Elaine Hasty and I'm the Senior Analytical Applications Chemist for CEM Coporation in Matthews, North Carolina in the U.S. Thank you for the opportunity to speak to you today about microwave digestion and elemental analysis of various food products. I just want to give you a quick introduction about who we are. CEM was established in 1978 by a chemical engineer, an electrical engineer, and a mechanical engineer. And they took their three disciplines and formed CEM Corporation. We're the oldest and largest microwave sample preparation company in the world, and we're headquartered in Matthews, North Carolina in the United States. All of our manufacturing, engineering, application support, service, and sales support are located here at the main campus in Matthews, North Carolina. However, we have 6 global subsidiaries and over 60 dealers worldwide to service and support our customers. With over 50,000 instruments sold, you've probably used or consumed a product that has been tested with a CEM instrument. As consumers, we want to be sure that the food we eat and the food that we serve our families is indeed safe. And there are regulatory agencies and government bodies in many countries around the world that have a legal obligation to protect the public health and ensure that our food is indeed safe. In the United States, that falls under the responsibility of the U.S. Food and Drug Administration, or the FDA. And they put together the Elemental Analysis Manual that details methods for testing of food products. And we want to focus on 2 of those methods today. One is method 4.7 for the analysis of 11 elements by ICP-MS, and method 4.4 for the analysis of 22 elements by ICP-OES. The same closed vessel microwave digestion method is used to prepare samples for both of these methods. These are the samples that we included in our study, and they consist of samples that were purchased at a local grocery store, as well as standard reference materials. We wanted to choose foods that were compositionally different in terms of their content of proteins, carbohydrates, and fats. And you can see on this food pyramid that we mapped the different protein, carbohydrate, and fat content of all of our samples and our standard reference material. So again, you can see a very diverse group. This chart shows the sample flow that we used in the process. Some of our samples required homogenization, which we'll discuss a little bit later, followed by closed vessel microwave digestion. The scope of the method involves transferring an analytical portion of our sample to a microwave digestion vessel, adding reagents, digesting the sample at 200 degrees, adding hydrochloric acid after digestion, either dilute hydrochloric or concentrated, and then diluting to a final mass. More specifically, we weighed out 1/2 gram based on a dry weight equivalent of our sample, or 5 ml of a liquid sample. That was our adult nutritional beverage. We added 8 ml of concentrated distilled nitric acid, 1 ml of 30% hydrogen peroxide, and after digestion, we added 1/2 ml of concentrated hydrochloric acid distilled to stabilize mercury, and then diluted to a final mass of 100 grams. Here again are the samples that we selected for our study. We purchased 10 samples at a local grocery store, and each of those samples were digested in duplicate for a total of 20 samples. 2 of those samples, the beef jerky and the gummy bear, were fortified with a low-level spike and a high-level spike, and each of those were digested in duplicate for an additional 8 samples. We included 3 NIST standard reference materials, and each of those were digested in duplicate for an additional 6 samples. And we included 2 method blanks and 4 fortified method blanks, 2 with a low-level spike and 2 with a high-level spike. So that gave us a total of 40 samples in our batch. So if you're a high-throughput lab, you get a lot of variety of different types of food samples in to test. You want to be able to process as many samples as you can, as quickly as you can, including your QCs, your SRMs, your method blanks, and in our case, that accounted for half of our batch. So you need a high throughput system that's going to allow you to process these samples, and the MAR6 iWave system with a 40-place 75 ml express vessel set does just that. As I mentioned before, a couple of the samples required some prep work before the prep work. We need a homogeneous sample that's representative of the entire food product. So for the frozen pizza and the chicken pot pie, where do we take the samples from? Do we sample the pepperoni? Do we sample the cheese? Do we sample the crust? For the frozen dinner, do we sample the vegetables, the chicken, or the crust? So what we did was we took the entire pizza, we took the entire frozen chicken pot pie and put them in a food processor and we blended them, and then we took half a gram of the blended product that you see in the jar for our sample. But you want to be mindful of the sample preparation equipment, the grinding equipment that you use to prep the samples. Most kitchen type blenders contain stainless steel blades, and that can potentially contaminate your sample. The FDA manual does address this, and they recommend either tungsten carbide or titanium blades to prevent contamination of the sample. One of the quality control checks required by the FDA method is to fortify or spike both samples and method blanks. These fortified samples and blanks are carried through the entire closed vessel digestion process, and then they're analyzed periodically throughout the analytical part in order to ensure data accuracy. In our study, we randomly chose the beef jerky and the gummy bear samples to fortify. This table shows the elements and the concentrations of the spiked solutions. Included are the big four: arsenic, cadmium, mercury, and lead; volatile elements: arsenic, selenium, and mercury; a mix of nutritive and non-nutritive elements. So this is a good test for the robustness of the method. Some of the samples in our study posed a bit of a problem when weighing and transferring into the vessel liners. Weighing is a very important step, as is every step in the process, but if the sample weights are not correct in the beginning, then the data that you get out of the ICP in the end is totally meaningless. So it's very important that you get an absolute quantitative transfer of your sample from the analytical balance into the digestion vessel. Some of the samples that we had problems with were powders. We all know that Teflon has a tendency to develop a static charge on the outside, so this can wreak havoc when you're trying to transfer dry powders from a spatula or weighing paper into a digestion vessel. Some of the samples that have a high moisture content, like the meat homogenate or the blended frozen dinner, are sticky, and they have difficulty getting to the bottom of the digestion vessel, which is where they need to be in order to be completely covered with your acid and to get a good digestion. Some of the larger samples, like the gummies, required cutting in order to get the appropriate half-gram sample weight. So here are some solutions for these types of problems. For the powdered samples, an antistatic ionizer works very, very nicely to dispel the static charge on the Teflon liners. You simply place the Teflon liner in front of the ionizer for a few seconds to neutralize the static charge, and then the powders will fall to the bottom of the vessel. CEM does offer an antistatic ionizers, but there are a lot of different ones on the market as well. For the sticky samples, we like to use metal spatulas or plastic scupulas in order to get the samples all the way to the bottom of the liner. If you are using a metal spatula, you do want to make sure that it's Teflon coated to avoid potentially contaminating your sample. For the larger samples, like our gummy bears that require cutting into smaller pieces, you want to use non-metallic scissors, such as ceramic scissors shown here, in order to reduce the sample size so that you can get your half-gram portion. We have more tips and tricks available in a video series called In the Lab that's located on our website, and we invite you to check them out. This is the equipment that we use to digest the samples in our study. We use the Mars 6 iWave digestion system and the 75 ml Express vessel set. The iWave features a contactless temperature sensor that measures the temperature in all of the vessels. It's simple to use, there's no connections to make. You simply load your vessels into the turntable, place the turntable inside the cavity, close the door, and you press start. It's that easy. There are sensors that will detect vessel type and the number of vessels, and this makes method creation easier because there's less decisions for the operator to have to make. There are pre-programmed one-touch methods that are ready to use, or you can program in your custom method with specific parameters such as those that are specified in this particular FDA method that we're using. The Express vessels consist of a simple three-part design that's easy to assemble. So what we have here is a high throughput system that's easy to operate. Here are the digestion parameters that we followed as specified in the FDA method. We used a half-gram dry weight sample or 5 grams of liquid samples, To that, we added 8 mL of concentrated distilled nitric acid and allowed the samples to pre-digest in the open vessels for about 15 minutes. Whenever you add nitric acid to food samples, especially those that are high in carbohydrates and sugars, you're going to see an immediate reaction. And that may be in the form of foaming or off-gassing. And that's because these compounds are easily oxidized and they're going to begin to digest right away, even at room temperature. So you want to let all of that initial reaction subside before proceeding to the next step. After that, we added 1 ml of 30% hydrogen peroxide and again let the sample sit open for about 15 minutes to complete all of the initial pre-digestion. At that point, the vessels were sealed and placed inside the microwave cavity. The heating program consisted of a 25-minute ramp to 200 degrees and then maintain 200 degrees for 15 minutes. Add to that an additional 20 minutes of cool down time, and in an hour you have processed a total of 40 samples start to finish that are now ready to be diluted for analysis. Here's a snapshot of our run in progress, and this is about 10 minutes into the ramp up to 200 degrees. If you'll notice, the batch temperature is now at 110 degrees, and that represents the average of all 40 samples in our batch. This is just below the boiling point of nitric, so if you were working on a hot plate, this is about where you would be digesting your samples. The temperature of each vessel is represented here on the bar graph, and you'll notice that the temperatures are quite uneven. Well, why is that? Well, think back to our food pyramid. Our samples are composed of proteins, carbohydrates, and fats, and all of these compounds have different characteristic temperatures at which they begin to decompose. Carbohydrates start to decompose around 140 degrees. Proteins are a little higher, about 150, and lipids are the higher, even still, at about 160 to 180 degrees. And the oxidation of organic material is an exothermic process, so samples that are high in carbohydrates and sugars, like our milk powders and the donuts, are going to start decomposing first and at lower temperatures than the samples that are higher in protein and fat, like the beef jerky and the cheese samples. And this is a very typical heating pattern when you're batching samples together that are compositionally different. Fast forward to the end of the 15-minute hold time, and we see that the batch temperature did achieve 200 degrees. We also see, according to the bar graph, that the temperatures of our vessels have evened up quite a bit during the hold time, but they're not perfectly even. Again, that's because our samples are compositionally different. We've also included in our batch some method blanks and spike blanks, and those samples don't go through the same exothermic process as our food samples do, so their heating profile is going to be a little different as well. But the intent of the method is for every sample to reach the minimum temperature that will completely digest every sample in the batch. So this method at 200 degrees does achieve that. Following digestion, the samples were allowed to cool to less than 50 degrees as specified in the FDA method, and that took about 20 minutes. At that point, the vessels were vented and opened, and the contents were quantitatively transferred to sample tubes and diluted to about 50 grams with 18 megaohm deionized water. To that, we added half ml of concentrated distilled hydrochloric acid to stabilize mercury, and then the samples are diluted to a final mass of 100 grams with deionized water. And as you can see in the picture, all of our samples were clear and colorless and particle-free, with the exception of one. When the powdered donut samples were diluted, they appeared to be very slightly hazy, and upon standing, we started noticing some fine white particles settling out, and we saw that in each of the duplicates. Based on the composition of the donuts, they should have completely digested with nitric acid and peroxide at 200 degrees. So what's different about this sample than all the others? Well, we know that some foods, especially powders, can contain inorganic anti-caking agents such as silicon dioxide and titanium dioxide. So we started thinking about the ingredients, and we checked the label on the donut bag, and sure enough, there's the titanium dioxide. Not only is it an anti-caking agent, but it also adds texture and brightness to food. So if you're making a white powdered donut, it makes sense to add the titanium dioxide. But for us, it's a problem because it's not soluble in nitric, peroxide, or hydrochloric. And we know that we need a little HF for dissolution of the titanium dioxide. So the question now is, do we add HF or do we not? And the answer is no, because it's not part of the scope of this method. So when you have inorganic particulates like this, you can simply let them settle out or filter the particles prior to analysis. So now that we've completed our sample flow for prep, we've homogenized our samples, we've digested them in the microwave, we've diluted them to volume, they're now ready for analysis. We'll look at method 4.7 first, which is the analysis of 11 elements by ICP-MS. And in our study, we use an Agilent 7800 instrument. Method 4.7 is applicable to food samples that are primarily composed of lipids, carbohydrates, and proteins, and is validated for 11 elements, including chromium, manganese, nickel, copper, zinc, arsenic, selenium, molybdenum, cadmium, mercury, and lead. It's not applicable for samples such as dietary supplements or foods that are high in siliceous content. It's also not applicable for speciation or elements including iron, magnesium, silver, iodine, and calcium. There are several quality control checks that are outlined in the FDA EAM method, and one is to run standard reference materials as part of your batch. You want to choose a reference material that's appropriate for the samples you're working with in terms of the matrix, the analytes, and the analyte concentrations. So for example, you wouldn't want to run an oyster tissue SRM if you're looking to analyze apple juice. The pass-fail criteria for reference materials is that the recoveries must be within 80 to 120% of the certificate values. This chart shows recoveries for our 3 SRMs that we included in our study, and that was the meat homogenate, the non-fat milk powder, and the slurried spinach. And you can see that the concentrations recovered were in good agreement with the certified value and all passed that 180 to 120% pass-fail criteria. The next check is to fortify a method blank, and this tests for non-spectral interferences or matrix effects. And that consists of spiking a method blank and carrying that through the entire method procedure from digestion to analysis, and is analyzed periodically throughout the analytical method. The acceptable recovery range is 90 to 110% of the spike value. And then this table will see the recoveries for our 1 ppb spikes, and all of them pass the 90 to 110% criteria. The last QC check consisted of fortifying analytical portions, and that consisted of spiking a known amount into some random samples and then carrying those spike samples through the entire procedure, again from digestion all the way through analysis. Spike values should be between 50 and 300% of the native levels, and the acceptable recovery criteria was 80 to 120% of the spike value. Shown here are recoveries for the beef jerky and gummy bear samples containing the 1 ppb spike. And for all elements, the spike recoveries were within plus or minus 20% of the spike value. So all 3 of the QC requirements, the SRMs, the fortified method blank, and fortified analytical portions have been achieved, and now we can have confidence in our analytical data for our unknown samples. Shown here are quantitative ppb results for the 11 elements as specified in the FDA method for 6 of the 10 food samples in our study. We also looked at some rare earth elements, as we know that they can cause potential interferences with arsenic at mass 75 and selenium at mass 78. But based on the low concentration of rare earths detected in our samples, they're very unlikely to cause any issues. For all of you chocolate lovers, we did notice something very interesting in our dark chocolate. We did notice higher cadmium levels versus all of the other food products. Chocolate is known to contain cadmium, which can be present in soil in some of the cocoa plantations. While the U.S. does not set a limit of cadmium in chocolate, the European Union does have a limit of 800 ppb for dry cocoa solids that are greater than 50%. So our level of 205 ppb is well below that limit. The FDA in the U.S. does recommend a maximum lead concentration of 100 ppb in candy that is likely to be consumed frequently by children. And so our level of detection in our dark chocolate and also in samples like the gummy bears was well below that limit. Let's turn our attention now to EAM method 4.4, which is analysis by ICP-OES. In our study, we used the Agilent 5900 ICP-OES system. The same samples that were prepped and run by the ICP-MS method were then run by the ICP-OES. The same quality control checks that were used in method 4.7 were used in method 4.4 to ensure data accuracy. If we start with the standard reference materials, We see that the recoveries for the spinach, the milk powder, and the homogenate were all in good agreement with the certificate values and fell within the 80 to 120% criteria, all with the exception of nickel in the meat homogenate, which was just a little bit high. The next QC check was the fortified method blank, and all analytes fell within the 90 to 110% recovery of the 50 ppb spike value. The last QC check was the fortified analytical portions, and here we see data for the beef jerky and the gummy bear samples containing a 50 ppb spike. And again, all elements were within the 80 to 120% of the 50 ppb spike value. Shown here are recoveries for elements that were not included in method 4.7, and they're shown for 6 of the 10 samples in our study. And these include the native concentrations of elements in the beef jerky and the gummy bear samples. That concludes this presentation. I would like to thank my colleagues at CEM, Macy Harris and Leanne Anderson, and my colleagues at Agilent, Jenny Nelson and Greg Gilliland, for their help in this study. And thank you for your attention.